So, Assalamualaikum and a very good morning, everybody. Today, we're going to be looking at the next topic in our heat transfer, which is principle of heat flow in fluids. So, previous class, we have looked at conduction for plain wall, one layer, plain wall, multi-layer, cylindrical pipe or tube, one layer and multi-layer, and also spherical for one layer or multi-layer. And we have discussed how we got the equation of Free's law and how the equation can be derived and how it can be used and can be developed for different conditions. So I hope you were able to follow the discussions that I've made so far in the class. So today we're going to be looking at the next topic, which is convection. So we have radiation, convection, and conduction. So today we're going to be focusing on convection heat transfer. So we have already defined what is convection heat transfer. So today is just a revision and revisit of the definition. So the flow of heat associated with the movement of fluid, such as when hot air from the furnace enters the room, or the transfer of heat from hot surface to the flowing liquid. So you can see here in this figure, you have initially you will have, let's say, hot water with low density and then cold water with high density. So what will happen here is that because hot water with low density will try to move upwards and the cold water with high density will try to move downwards. So whenever you are supplying heat to the water, water will become hot and it will become less dense, so it will move up. So the water on the top, which has the cold water, which has a higher density, so it will move down. So this process will be in a circle. Okay, and the second one is that when you have cold air and let's say you have a vapor going in on the other direction, so the cold air will become hot air and the vapor will become cold vapor. So this is basically the definition of convection. So for conduction, we define conduction, the equation related to conduction was Free's law. For convection, the equation related to the convection heat transfer known as Newton's law of cooling. So this is the equation that we will use for convection. Q is over A is equal to H Ts minus Tf. So again, the Q here is our heat transfer rate and the unit here is watt, and then our value of A is our area, and then just give me a moment. I was saying Q is our value of heat transfer, which is the unit of W. A is our area of heat perpendicular to the direction of heat transfer. Ts is the surface temperature or the wall temperature. Tf is the fluid temperature. So I just put here Kelvin and Kelvin. It can also be in degrees Celsius or in Fahrenheit or in Rankine. And then H is a new term that we are introducing today, which is known as heat transfer coefficient. And the unit is going to be watt per meter squared, degree Celsius or degree Kelvin. So remember, I mentioned to you in the first class and second class, we are focusing on K, H, and U. So K is related to conduction. And now H, we are introducing today, is actually related to convection. Okay. So unit of K we know is going to be watt per meter Kelvin, but unit of H is going to be watt per meter squared Kelvin. So you have a difference between unit of K and unit of H. So you must be able to remember the unit of K and unit of H, because after this we're going to be combining both H and K into one equation. So it is very important that you can differentiate what is the value of K and what is the value of H, and what is the definition of K and what is the definition of H. Okay, so this is the equation that we'll be using for now. So again, convection, we can have two types of convection. We can have natural convection, or we could also call it natural convection, or we can have a forced convection. So forced convection and natural convection can happen without phase change and with phase change. Meaning that if let's say you have, for example, steam. So steam initially will be in your gas form. So when you have a forced convection, when the heat from the steam is transferred to the surface or to another liquid, where a convection process happens, the steam can remain as steam or it can change into water. So if it remains as steam, for example, in our case for forced convection, if the steam remains as steam, even though it has transferred some of the heat to another fluid or a surface, so we can say is that forced convection without any phase change. If the steam is already transferred heat from and to a surface or to a fluid, and then it is condensed into water, so we say forced convection with phase change. So the phase change is here is referring to the condition the steam is on the final. Okay, so free convection meaning that you have no external forces acting on your fluid, whereas forced convection there will be external forces. So you can see here we have the same setup. In one, you don't have any kind of force to mix the hot and cold liquid, but here we have an agitator. So actually this is our force that we are actually putting on the water. So this is what we call forced convection, and this is what we call free convection or natural convection. So this is example number 1. So this is just to familiarize yourself with the equation. So it's saying that air at 20 degrees Celsius, so this is the temperature of air, blows over a hot plate 50 by 75 cm maintained at 250 degrees Celsius. The convection heat transfer coefficient is 25 watt per meter squared degree Celsius. Calculate the value of heat transfer. Okay, so if we were to draw this surface, okay, so it will be like something like this. Let's say this is your hot plate. Okay, the temperature of the surface, so this is the wall temperature or the surface temperature, Ts is equal to 250 degrees Celsius, and then we have air at 20 degrees Celsius. So let's say this is your airflow. So air at T, so air is our fluid, so Tf is equal to 20 degrees Celsius. It's flowing, and then we know that heat transfer coefficient, so the value of H. Okay, so the way you want to identify whether this is H or K, the easiest way is that you look at the unit. If it has a unit of watt per meter squared degree Celsius, so this is your whose mic is not mute. Okay. Lilian, I think your mic is not mute. Okay, sorry for the interruption. So as I was saying, so still not mute. Anybody tell her to mute her mic? Do I have to mute my mic? Let me just mute her mic. Okay, sorry for the interruption. So where was I? About our heat transfer coefficient. So the easiest way for you to differentiate between H value and K value is that you just look at the unit. If the unit is watt per meter squared degree Celsius, you know that it will be your value of H, because sometimes we can call it the convective heat transfer coefficient, or sometimes we just say heat transfer coefficient or convection heat transfer coefficient. So it has different names. So the best way for you is to that just look at the unit. So we can say here the value of H is 25 watt per meter squared degree Celsius. So if you look at the equation just now, Q over A is equal to H T surface minus T fluid. So this was the equation. But the question is asking us to find the value of heat transfer. So Q over A has a unit of watt. So you have to change the equation first. So Q is equal to H A T S minus T F. So to find the value of A, so you're given the dimension of A 50 times 75. So 50 times 75, or change it into meters. So 0.5 times 0.75. So you get a value of 0.375 meter squared. So if you look at the equation, you know the value of H, you know the value of A, you know the value of T surface, which is your wall temperature, and then you know the value of T fluid, which is your temperature of air. So you substitute everything. So 25 watt per meter squared degree Celsius times the value of A is 0.375 meter squared minus your value of 250 minus 20 degrees Celsius. So cancel out degree Celsius with degree Celsius, meter squared with meter squared, and then you only leave with the unit of watt. Put in your calculator and then you'll get a value of 2156 watt. So that is how you solve example number 1. Okay, so this is very basic, very simple, just to familiarize yourself with the equation of Newton's law of cooling. So I have here example number 2. So please go back and try, and once you have tried, you can ask me whether you are doing it right or wrong. So read the question properly. Hot air at a certain temperature is flowing over a flat plate maintained at a temperature of 150 degrees Celsius. The convective, say this is the second way we can call the value of H. The convective heat transfer coefficient is 75 watt per meter squared degree Celsius, and the heat flux, so this is heat flux, is 7500 watt per meter squared. Calculate the temperature of air flowing over the flat plate. So you want to find the value of Tf. So this is the heat I'm going to give you. So go back home and try these questions. Okay. So now that was for convection. So later on, after this topic, we'll be focusing more on convection. But for now, this is just the introduction for convection. Because for today, we are more focusing on the combination of heat transfer, which is the combination of conduction and convection. So again, I'm just listing down all the properties of conduction and convection. So conduction happens predominant in solid. Heat is transferred by the free electron movement or molecular vibration, and the equation is Furier's law. Whereas convection predominant in fluids such as liquid and gas. Heat transfer by the motion of fluid, and the equation governing the convection is Newton's law of cooling. So usually we have looked at conduction on its own and convection on its own, but most of the time conduction and convection happens at the same time. So if you look at this pot of water that is being heated up, so first of all you will have direct contact. So this wall will be heated up by conduction, and then this wall will transfer its energy. Heat is transferred. So first of all you have conduction here, and then from conduction, from the surface of the inside wall, you'll have convection from the surface wall to the fluid. So that is why we call it is a combination of conduction and convection. So when we have a combination of conduction and convection, we will have to find a new coefficient. So some of the examples of heat heat transfer equipments are heat exchanger. So this you will be focusing more on Dr. Halina's part. You will learn more in detail about how to design heat exchanger and how to calculate all the properties involved with heat exchanger. But for today, I'm just going to be showing you the basic examples. Okay, so we can have different type of heat exchanger. So this is what we call double pipe heat exchanger, meaning that you have a double pipe system where you have one fluid. Let's say this is fluid A. Okay, this is fluid A. Fluid A is flowing in one pipe, and then fluid B is flowing in the other pipe. So you have double pipe heat exchanger. So the function of heat exchanger is to, it's in the name, heat exchanger is to exchange heat. Okay, so you want to exchange from fluid A to fluid B or fluid B to fluid A. So this is certainly is a lot have been used in the industry for heat transfer purposes. And then this is the second example, single pass tubular condenser. So we can call it condenser or heat exchanger. When you say condenser, you have something you want to condense. For example, you have a vapor and you want to condense it into water. So you pass it through, this is what we call shell and tube, because you have a big shell and you have a small tube inside it. So inlet liquid and then outlet liquid and then inlet vapor and outlet condensate. So this is also a type of heat exchanger, but since the function is to condense your hot vapor into liquid, so we call it condenser. And then this is, I'm just going to go through because all these things you will be learning with Dr. Halina. So in heat exchanger, we can have two type of flow. The first one is counter current flow. The second one is parallel flow. So counter current flow meaning that if you look at this figure or this figure, you will have either fluid going in the same direction or fluid going in the different direction. So let's say this is for your counter flow. Okay, counter flow meaning that, let's say you have a double pipe system. Okay, so this is the first pipe, this is the second pipe. So if let's say it is counter flow, your one fluid A is flowing in the left to right direction, whereas another fluid B is flowing from the right to left direction. So this is what we call counter flow, counter current flow. Is that the fluid is going into the heat exchanger at a different side. Whereas if you have for parallel flow, so the same thing, let's say you have a double pipe heat exchanger. So if fluid A is flowing in left to right direction, fluid B also is flowing from left to right direction. So you can see here, that's why you have, so we define our temperature. So whenever you have heat exchanger, you will have 4 temperatures, because you will have 2 temperatures for fluid A and 2 temperatures for fluid B. So we define here as THA, THB, TCA and TCB. So THA is defined as the TH is the T temperature hot. A is for the fluid entering the heat exchanger. So temperature of entering hot fluid. So THA is temperature for the hot fluid at the entrance. THB is again T hot, but is for the hot fluid leaving, the temperature of hot fluid leaving. So THB. TCA, C stands for cold. So TCA is the temperature of hot of cold fluid entering the heat exchanger, whereas TCB is the temperature of cold liquid leaving the heat exchanger. So you have THA, THB, TCA and TCB. So you will be introduced to this term which is called delta TM. So delta TM is actually log mean temperature difference, or we call it in short form is LMTD. So this delta TM or LMTD will be used when you are designing your heat exchanger equipment. So this is one of the important temperature that you will be using in Dr. Halina's class. But for today, I'm just going to be introducing you to the concept of LMTD. So LMTD is equal to delta T2 minus delta T1 over ln delta T2 over delta T1. So you have to be able to identify what is delta T2, what is delta T1 based on your type of flow. So let's say if you have counter current, this is your delta T2 and this is going to be your delta T1. If you have co-current or parallel flow, this is going to be your delta T2 and this the whole thing here is going to be delta T1. Once you have identified it, you can find your LMTD temperature, and based after that you can just find the value of your Q or A, whatever is required for you to design the heat exchanger equipment. Okay, so this is basically just another part which will be used. So the energy balance in a heat exchanger equipment. In heat exchanger, there is no shaft work and mechanical potential and kinetic energy are small in comparison with the other terms. So this is one of the equations you can use to find your value of Q in heat exchanger. Q is equal to m dot. M dot is the mass flow rate of the stream. HB minus HA is the enthalpy. Okay, and Q is the value of heat transfer. So once you know this one, so you can have Q for the hot liquid and Q for the cold liquid. It will be the same number but different direction. Okay, so if you think logically, your QC must be a positive value. Why? Because your QC here is the heat transfer to cold liquid, meaning that your cold liquid is receiving an amount of heat. So that's why the QC is a positive value. Whereas your QH is the hot liquid which is losing the heat, because it is giving the heat to the cold liquid. So that's why we have QC is equal to negative QH. The QH value will be a negative value. Or you can say that QH is equal to negative QC. Either way, QC is a positive value, QH is a negative value. So, but the numbers is the same because we are saying that it is still steady state. Meaning that if it's steady state, then whatever amount of heat is transferred from the hot liquid is received by the cold liquid. So again, this is if you are using enthalpy. You can also use the THA, THP, TCB or TCA. So again, if you look at here, your THA is a big value, THB is a small value, TCB is a big value, and TCA is the small value. So you'll get a value of positive for your QC and negative for your QH. So CP is the specific heat for cold liquid, CPP is the specific heat for hot liquid, and THA, THB, TCA, and TCB are the temperature of hot or cold liquid entering and leaving. Okay, so now this is the main part of our class for today. Remember, I said that usually whenever you have, let's say this is a cross-sectional area of your tube, okay, one liquid is flowing inside, one fluid is liquid flowing outside. Okay, let's say we have a counter current flow. So they say that, let's say inside here is hot, outside here is cold. So whatever heat is being transferred is going to be transferred from the cold liquid, from the hot liquid to the surface, and then to the surface to the through the thickness, and then from the thickness to the cold air or whatever. So you can say here from this point to this point, for this area it is convection. Okay, through the thickness of your pipe for this part is conduction. And again, after the outer diameter, outer surface of your pipe, it is going to the air, it is convection again. Okay, so if you look at here, this is, so what does it mean here? This is actually the thickness. So we just cut your pipe and make it into a flat pipe. So you will have inside thickness and outside of the pipe. So from, you can see here, for the inside of the tube, the heat transfer, okay, from the inside of the tube, this is the inside. So this is your T inside, okay, TA. So what is happening here? This is being, the heat is being transferred by convection to the wall of the tube. So for the inside tube, H inside is equal to dQ over dAI TH minus T wall hot. Okay, so TH is your initial temperature, and then T wall hot is the temperature at this area. Here, this area. So this is your T wall hot. What is happening? Hold on, I'm having some issues. Okay. So again, this is your T wall hot. This is your T hot. So then after that, after heat is transferred from the hot liquid to the surface of the pipe, it will be transferred from this thickness, okay, according to the thickness of the pipe. So this is transferred by the conduction. So you see here the rate of heat transfer to the tube wall. dQ over dL is equal to K TW hot minus TW cold over XW. So depending on the thickness. So this is your conduction. And after that, the heat again will be transferred from the outside wall to the outside by convection. So from the outside tube to the cold side, so this is your, let's say this is air or any other fluid, this will happen by convection again. So you have H inside, H outside. So H outside, HO is equal to dQ over dA over TWC minus TC. So now we are trying to combine your HI, HO, and also your Km value. So once we combine this, we know that delta T here is equal to TO minus T, no, TI minus T outside. T inside minus T outside is equal to your delta T. So you don't need to actually remember how to derive this equation, but we combine everything and then we do some unit rearrangement and integration and differentiation. So finally you'll get a value of UO. Okay, so UO is equal to 1 over HI dO over dI plus XW over Km dO over dL plus 1 over HO. So this UO is known as heat transfer coefficient. Okay, so remember we had K, H, and U. So you can say that K is for conduction, H is for convection, and U is for conduction plus convection. So this is a very important heat transfer coefficient, and we call it U as overall heat transfer coefficient, meaning that it covers whatever heat is flowing from the hot fluid from here to the cold fluid, which is here. So the combination of convection, conduction, and convection, we get the value of U. Now you see here we have UO, meaning that so UO is considering the outside surface area. So you look at here, I've labeled inside and outside. So inside surface area and outside surface area, there will be a difference because you have a different diameter. So remember, if let's say we just draw a circle and we draw a tube, so this is your inside diameter and this is your outside diameter. So when we are saying UO, overall heat transfer coefficient based on the outside surface area, so we are talking about UO is over here. If I have UO, then I can have UI. So UI will be based on this inside surface area. So you have UO and UI. So you can see here, there will be a difference between UO and UI because there's a difference between the surface area on the outside and surface area on the inside of the tube. Why is there is a difference? Because the diameter inside is smaller than the diameter outside. Okay, so again, if you have UO, then you have UI. So UI is equal to 1 over HI plus XW Km DI over DL plus 1 over HO DI over DO. So you don't have to actually remember the equation, but you have to know what is each term means. So HI is the heat transfer coefficient on the inside. XW is the wall thickness. Km is the thermal conductivity of the wall. Di is the value of diameter inside. Dl is an average diameter. Ho is the heat transfer coefficient on the outside. Di is the inside diameter and Do is the outside diameter. So this is how we get our value of U. Now to get the value of Q. So this is the equation for Q. dq over dA is equal to U delta T. Now delta T here is referring to T inside minus T outside. Whatever hot minus cold temperature. And this is just, I'm just putting this as a analogy. So if you see here, this is our equation for plane wall. Q over A is equal to delta T over R. But if you look at for the overall heat transfer coefficient, you have dQ over dA is equal to U delta T. So it means that we can say here the U here is actually equal to 1 over R. If you compare this equation to this equation, so that is why I just put that R is equal to 1 over U. So but for you can just use this equation. If the question is asking you to find the value of heat flux, so dQ over dA is equal to U over delta T. Okay. So I would like to explain a little bit further on this equation. Okay, so remember we are still on steady state. Okay, we are not on unsteady state. So under steady state, we are saying that delta U over 1 over U. So you must be able to define what is delta T, what is delta Ti, what is delta Tw, and what is delta To. Why this is important? Because you have to be able to identify where does this temperature difference comes from. Okay, so for delta T is always going to be T hot minus T cold, meaning that the largest temperature minus the lowest temperature. The largest temperature must always be on the warm liquid side, warm fluid side, and the cold temperature will be on the cold liquid side. So largest minus smallest. and then it will always be the bulk temperature. So hot minus cold. Now if you look at delta Ti, so we can label here, this is inside, this is outside. Okay, so when I say delta Ti, I mean the temperature difference on the inside. So we are just focusing on this part. So if you look at here, if you want to find delta Ti, you have two temperature, T hot and T wall hot. So again, delta T must always be big minus small. So it is T hot minus T wall hot, or T hot wall, depending on whatever you want to write. Okay, so that is for delta Ti. So delta Tw is actually referring to the temperature difference across the wall or across the thickness of your material. So actually this is referring to this here. What is the temperature difference from this point to this point? So if you see the figure, you can know that the temperature delta Tw is actually equal to T wall hot minus T wall cold. Okay, because this is a bigger temperature, this is a smaller temperature. And then finally we have our delta TO. Delta TO is equal to T wall cold minus T cold. Okay, so you must be able to identify which temperature referring is to which part of this equation, because sometimes the question might ask you to find the temperature of the hot surface. So if I say temperature of the hot surface, I'm referring to the temperature over here, which is your T wall hot. So in order for you to find the T wall hot, you must use one of these equations. Either delta TO is equal to delta Ti di over do, or any other things. So you must be able to first of all identify which temperature you want to find. After you have identified, then you can choose whether you want to use this part of the equation or you want to use this part of the equation. Okay, so you must be able to identify what is the definition of each delta and each temperature. Okay, is there any questions?
Not that.
Okay, if no questions, so I'll just go a little bit further, just 5 more minutes. Okay, so usually you see that we had our initial equation where we have, let's say for UO, we have 1 over HI, DI over all these things, but now we are adding another factor which is called the fouling factor. Okay, so the fouling factor, for it you just have to add another term which is known as the fouling factor HD. So what we mean is that usually, let's say this is your cross-sectional area just now. So initially you will have hot, liquid, and then convection, conduction, and convection. But after a while, there will be fouling, meaning that sometimes there will be some kind of sedimentation on this wall and also on this side of the wall. So convection, then there will be some resistance here and then some resistance here, and then only you have your heat transfer. So in order to take into account this, so we are adding another heat transfer coefficient which is known as HD. So HD is for your fouling. Okay, so you will have HDI and HDO, fouling on the inside and outside. So depending on your question, whether it is asking you to find the value of UO or UI, so you have to use the appropriate equations. Okay, so that is for this one. So this is the important expressions that you have to understand. You don't have to memorize, but you have to understand what are the terms involved in these equations. So the first one is that u on the, this one should be outside, okay, and then this one u outside with the fouling factor, this one is u inside, this one is u inside with the fouling factor, and this is the equation you will use to find the value of dl, and this is the equation that you can use to find the value of your delta T or any temperature at the interface. So I have written everything here. UO, what is the definition of UO? Is overall heat transfer coefficient on the outside surface area. UI, overall heat transfer coefficient on the inside. HI, heat transfer coefficient on the inside. HO, heat transfer coefficient on the outside. DI, fouling factor inside. DO, fouling factor outside. DO, outside diameter. DI, outside diameter. DL is the logarithmic mean diameter. XW is the tube or pipe wall thickness, and Km is the thermal conductivity of the wall or pipe or tube. So you have to understand and be able to differentiate one from the other. And before I forget, we know the unit of H, watt per meter squared, degree Celsius or Kelvin. We know the unit of K is watt per meter Kelvin or degree Celsius. You have to find out what is the unit of U. Okay, so this is a short assignment for you for today. What is the unit of U? Because I've been telling you from day one, correct answer must be together with the correct unit. So you must know what is the unit for U. Okay, so this is an example. So for this example, I have actually pre-recorded the solution. So I'll upload this to our e-learning and you can just watch it there. But if you look at here, just if you go through fast, water is flowing at a 50 degree inside the tube, so that the HI value is 3500. The tube have a wall thickness of 0.8 with a thermal conductivity of 16 watt per meter degree Celsius. The outside of the tube loses heat by free convection with a heat transfer coefficient of 7.6. Calculate the overall heat transfer coefficient and the heat flux surrounding the air at 20 degrees Celsius based on the outside area of the tube. So if you want to start everything again, start with labeling everything. So 50 degrees Celsius, this is your H inside. Oh no, sorry, T inside. This is your T inside. And then you know your HI, and then you know 0.8 mm is your XW with a thermal conductivity of 16. So this value is the value of your Km, the material thermal conductivity. The outside tube is losing heat by the free convection with the heat transfer coefficient of 7.6. So you can say this value is your HO. Calculate the overall heat transfer coefficient and the heat flux based on the outside surface area. So you want to find the value of the UO and also DQ on the outside. So this one also will be outside. So if you look at the questions, you know the value of HI, you know the value of DO, you know the value of DI, you know the value of XW, you know the value of Km, you know the value of DO. You can calculate the value of DL based on this equation, and then you know the value of HO. So you have all the informations. You just need to put in the equation and calculate the value. Okay, so this is example number 3, and then we have example number 4, and then we have example number 5. And then this is a question for final exam 2018 and 2019. So you can go back home and try it. And this one is actually to show you that sometimes in real life, this is how you get the value of your DO and DI. So if you look at the table here, it will give you the outside diameter. So this is the nominal pipe size. So usually this is how we classify our size, our pipe. Is it a 1 mm or 1 something or 2 or 3? And then based on that, we'll know this is your outside diameter. But if you see here, there is no inside diameter value. So how do you get your inside diameter value? Based on this wall thickness. So if you looked at example number 3, given the inside diameter of the tube is 0.025, but nowhere here the question gave you the value of, so DI is 0.025 meter, DO is not given. So how you calculate your DO? I have explained to you in our previous class. What is the relationship between DO, DI and XW? So please go back and try to solve these questions. Okay, so that is all for our class today. If you have any questions, you can ask me.